There is a place in our solar system of perfect radio silence. It is the far side of the moon, a shielded sanctuary from the ceaseless electronic noise of our own planet. This video will show you how a massive telescope built there could fundamentally rewrite our cosmic history. What if we could hear the faint birth cries of the very first stars, or detect the protective magnetic field of a distant Earth-like world? We are on the verge of listening to frequencies of the universe that have been hidden since the beginning of time. What do you hope we will hear in that profound quiet? Think of our planet not as a blue marble, but as a brilliant, screaming radio beacon. Every cell tower, every television broadcast, every radar sweep, and every satellite link creates a constant, chattering static that leaks out into space. This electronic hum is our civilization's signature, and it blankets the entire near side of the moon. It is an inescapable fog for any telescope trying to listen to the faint whispers of the cosmos. But step around to the far side, and that cacophony vanishes. The 2,000-mile thick body of the moon itself becomes the ultimate noise-canceling wall, blocking all of Earth's radio chatter completely. It is the only place in our entire Earth-Moon system where true radio silence is guaranteed. This isn't about finding a quiet spot in a remote desert. It's about stepping into a different room entirely and closing a vault door behind you. In that profound and engineered quiet, the universe begins to speak in voices we have never been able to hear. The static of creation fades away, and what remains could be the clear, undistorted signal from the dawn of time. That primordial quiet opens a window to our deepest past. For centuries, astronomers have pieced together the story of the universe by looking at light, but the very first chapter is written in a different language entirely, one of faint radio whispers. This chapter is called the Cosmic Dawn. It describes a time a few 100 million years after the universe began, when the long, cold, dark ages finally ended. Before this moment, the cosmos was a silent, opaque sea of simple hydrogen gas. Then, something miraculous happened. The first stars flickered on, not like the stars we see today, but colossal, brilliant beacons made only of hydrogen and helium, burning fast and furious. Their intense ultraviolet light began to energize the surrounding gas, a process that left a distinct fingerprint, a specific radio signal emitted by that primordial hydrogen. Think of it as the universe's first photograph, a snapshot of its infancy, but one that has been traveling toward us for over 13 billion years. During that unimaginable journey, the expansion of space itself has stretched that original signal. Its wavelength has been pulled longer and longer, like a note from a song slowed down to a deep, rumbling hum. That hum now falls into a part of the radio spectrum that, here on Earth, is completely drowned out. It is swamped by our own radio noise and even by the natural crackle of our ionosphere. This is why that signal has never been directly detected. It is the holy grail of modern cosmology, a message from the beginning of structure, and it is hiding in plain sight, just beneath a wall of static. A telescope on the lunar far side, sitting in that perfect silence, could be exquisitely tuned to listen for that one specific, deep hum. By patiently mapping its subtle variations across the sky, such an instrument wouldn't just hear a single note. It would create a three-dimensional map of the infant universe. We could see where the first pockets of gas began to clump together under gravity, tracing the scaffolding upon which all future galaxies, including our own Milky Way, would be built. This would be more than just a new picture. It would be a direct test of our entire understanding of cosmic evolution. Did those first structures form as our models predict? Or would this ancient map reveal surprises, showing us a dawn that was stranger and more beautiful than we ever imagined? but the story of the cosmos is not written only in the light of its first stars. The vast majority of the universe is made of things we cannot see, forces we do not feel, a hidden architecture that governs everything. We call these components dark matter and dark energy, and together they make up over 95% of all that exists. Yet they reveal themselves only through their subtle, ghostly effects on the ordinary matter we can observe. A lunar far-side telescope would become our most sensitive instrument for feeling those effects across the breadth of cosmic time. Think of the early universe as a vast, three-dimensional spiderweb with strands of hydrogen gas tracing the underlying structure. That web did not form randomly. It was sculpted by the gravitational pull of dark matter, an invisible skeleton that provided the framework for everything to clump together. By using that deep hum from the cosmic dawn to map the hydrogen with phenomenal precision, astronomers could essentially trace the shape of that invisible skeleton. They could see how dark matter filaments guided the flow of gas billions of years ago, testing our theories about what this mysterious substance actually is. Is it a sea of exotic particles, as many physicists suspect, or could the map reveal gravitational fingerprints that point toward something even more unexpected? The telescope's power would not stop in the distant past. As the universe aged, a different hidden force began to dominate its destiny: dark energy. This is the enigmatic pressure causing the expansion of space to accelerate, pushing galaxies apart from one another at an ever-increasing rate. To understand it, we need to measure how fast the universe was growing at different points in its history. Those deep radio signals from hydrogen are perfect cosmic mile markers. By observing how the signal's signature changes from the early universe to more recent cosmic epochs, scientists could create an ultra-precise chart of the expansion rate over billions of years. Each data point would be a new constraint, a fresh clue in the investigation. Is dark energy a constant force, as Einstein once proposed, or does its strength vary over time? The answers are written into the stretched light of ancient hydrogen, waiting in the lunar silence to be read. This would not be a direct picture of the dark universe, but something perhaps more powerful: a forensic examination of the entire cosmic crime scene. By studying how visible matter moved and was arranged under the influence of these invisible giants, we could finally begin to understand the true nature of the reality we inhabit. Beyond the grand architecture of the cosmos lies a more intimate search, one for other worlds like our own. While we have discovered thousands of exoplanets, we know almost nothing about their true nature. Are they barren rocks, or could they be cradles for life? A telescope on the lunar far side could provide a revolutionary clue by listening for a planet's invisible shield, its magnetic field. Here on Earth, our magnetic field is a silent guardian. It deflects the constant stream of charged particles from the sun, the solar wind, channeling some toward the poles to create the beautiful auroras. That interaction between a planet's magnetic shield and its star's wind does not just create light, it also generates a faint but distinct radio whisper. For the first time, a lunar observatory free from interference would be sensitive enough to potentially detect that specific radio signature from planets orbiting other stars. Think of it as tuning a cosmic radio to the frequency of planetary protection. Detecting this signal would be a monumental achievement. It would tell us that a distant world possesses a global magnetic dynamo, a churning metallic core like Earth's. This is not just a scientific curiosity, it is a fundamental requirement for long-term habitability. A strong magnetic field acts as a planetary umbrella, deflecting the erosive force of stellar radiation that would otherwise, over millions of years, strip away a world's atmosphere and evaporate its oceans. Mars serves as a solemn reminder of this process. Scientists believe the red planet lost its global magnetic field long ago, and with that shield gone, Its once thick atmosphere was gradually torn away by the solar wind, leaving a cold, desolate surface. Finding an exoplanet with a robust magnetic field would immediately elevate it on the list of promising candidates for life. It suggests a world that has likely maintained a stable climate and a protective atmosphere over geological timescales, creating the consistent conditions necessary for chemistry to become biology. This capability would allow us to move beyond simply counting planets in a star's habitable zone. We could begin to categorize them by their planetary integrity. Which worlds are armored, which have likely held onto their atmospheres and surface liquids for billions of years? A lunar far-side telescope could help us compile the first catalogue of shielded worlds, refining the ultimate search from one for merely Earth-like orbits to one for truly Earth-like sanctuaries. Yet the most profound signal a lunar observatory might find is one we have never sent. It is the search for intelligence beyond our own, a quest that has until now been conducted from within a storm of our own making. Every radio telescope on Earth, no matter how remote, must filter out the relentless static of human technology, a process akin to straining to hear a whisper at a rock concert. The far side of the moon offers the first true listening post, a place where the cosmic radio dial is free from our own station's overpowering broadcast. With that interference gone, an array there could be tuned with exquisite precision to listen for the signature not of nature but of technology. This search is not merely for a deliberate hello beamed toward us. It is a hunt for the inevitable byproducts of a civilization that has mastered radio, the same way our own planet has for the past century. Think of Earth as it appears from a few light years away, not as a blue dot, but as a shimmering bubble of artificial radio noise. Our television broadcasts, our radar, our satellite communications all leak into space, creating a faint but detectable technosignature that expands outward at the speed of light. An advanced society elsewhere would likely produce a similar radio halo, a telltale glow of organized energy use. A lunar far-side telescope, operating in pristine silence, could conduct the first truly systematic all-sky survey for these subtle, narrow-band signals. It would scan the entire cosmos with a sensitivity and clarity impossible on Earth, listening for the specific, non-random patterns that nature simply does not create. The power of such an instrument lies as much in what it does not hear as in what it might. Imagine turning this unparalleled ear to the galaxy and hearing only the natural chorus of stars and gas. A comprehensive, sensitive search from such a quiet vantage point that returns only silence would be a result of deep scientific importance. It would provide our first solid data point for a profound question, helping to constrain the possible prevalence of communicative, technological civilizations in the Milky Way. It would suggest that if they are out there, their signals are either too faint, too different, or perhaps they choose not to broadcast in ways we can yet perceive. This quiet answer would refine the search, guiding future efforts and reshaping our understanding of our place in a potentially lonely cosmos. The search itself, conducted from that silent lunar outpost, would become a testament to a species reaching out not with a shout, but with the most patient, attentive listening it has ever achieved. Our sun is not a placid orb of light, but a dynamic sphere of churning plasma, capable of sudden and spectacular violence. These solar storms, immense eruptions of energy and matter, are not just visual spectacles, they are powerful radio events that fill space with a crackle of static. From our vantage point on Earth, studying this radio fury is like trying to understand a thunderstorm while standing in the middle of it, surrounded by the roar. The lunar far side offers a unique escape, a stable platform in the deep quiet of space from which to observe the sun's tantrums with perfect clarity. Imagine having a front row seat to a solar flare, but one where you can also hear every note of its radio frequency scream without any background noise. This perspective is not merely academic, it is a matter of practical survival for our technological civilization. When a coronal mass ejection, a billion-ton cloud of magnetized solar plasma, erupts from the Sun, it races toward Earth at millions of miles per hour. The intense radio bursts that accompany it are a direct tracer of the most dangerous component, high-energy particles accelerated to nearly the speed of light. These particles can arrive at Earth in minutes to hours, posing a severe radiation hazard to astronauts in orbit or on the Moon, and can cripple satellites by frying their delicate electronics. By using a lunar telescope to meticulously study the low-frequency radio signatures of these eruptions, scientists could decode the precise mechanisms that launch these particles into space. They could watch the storm unfold from ignition to propagation, mapping how energy is transferred and particles are accelerated. This knowledge is the key to transforming space weather forecasting from a general warning into a precise prediction. Instead of simply knowing a storm is coming, we could learn its intensity, its particle composition, and its likely trajectory with far greater accuracy. For future lunar colonists, such forecasts would be as essential as checking the weather is for a farmer. A reliable warning could give them time to retreat to shielded habitats, protecting them from a sudden surge of radiation. For mission planners sending crews to Mars or beyond, understanding these solar particle events in detail is non-negotiable. The journey will take them far beyond the protective magnetic bubble of Earth, exposing them directly to the raw fury of the Sun. A telescope on the lunar far side, acting as a dedicated solar sentinel, would provide the foundational data needed to design safer spacecraft, plan mission timelines around solar activity, and ultimately ensure that humanity's expansion into the cosmos is not left vulnerable to the unpredictable moods of our nearest star. The sheer scale of this ambition confronts us with a profound challenge. We are not merely placing an instrument on another world, we are weaving a new kind of ear from the very dust of the Moon itself. The traditional model of a single, towering dish is impossible here. The cost and risk of landing such a fragile, massive structure are beyond consideration. Instead, the most promising design is elegantly simple in concept, yet breathtakingly complex in execution. It begins with thousands, perhaps even millions, of small, identical radio antennas. Think of them as tiny metal rods, no more sophisticated than an old-fashioned television antenna. These are the pixels of our new cosmic sensor. The plan is to deploy them across the floor of a vast, ancient lunar crater, a natural bowl that has waited in stillness for billions of years. The deployment itself is a ballet of robotic ingenuity. Automated rovers might crawl across the regolith, planting each antenna like a seed. Or, more fantastically, a lander could use a system that literally unspools long, flexible sheets of antenna material directly onto the surface, like laying out a cosmic welcome mat. The goal is to cover an area dozens of miles across with these simple receptors, transforming an entire lunar landscape into a single, unified instrument. This is where the true magic happens. Each individual antenna is not powerful on its own, but by linking them all together with a central computer, using a technique called interferometry, they can act as one. The distance between the farthest antennas becomes the effective diameter of the telescope. A network spread across a 50-mile crater creates, in essence, a single radio dish 50 miles wide. The resolving power of such an array is almost incomprehensible. It could discern details in radio sources with a clarity hundreds of times greater than anything possible on Earth. Powering this silent city of antennas presents its own lunar rhythm. During the 2-week-long lunar day, vast fields of solar panels would soak in the unfiltered sunlight, charging batteries and running operations. But when the long, frigid lunar night descends, lasting another 14 Earth days, the array would enter a state of hibernation. It would draw on stored power only for its most essential functions, patiently waiting for the sunrise to awaken and listen once more. This entire endeavor would be a symphony of autonomy. From deployment to calibration to daily operation, the system would need to function with minimal direct human intervention, a testament to the next generation of robotic explorers. Success here would do more than just build a telescope. It would prove the blueprint for constructing large-scale, resilient infrastructure on other worlds. It would show that we can use the local materials and clever engineering to create lasting tools for discovery, turning the challenges of an alien environment into the very foundations of a new scientific age. Building such a delicate instrument in this silent sanctuary means confronting the moon's harsh and deceptive nature. The very ground that offers perfect quiet is an engineer's formidable challenge. That gray dust or regolith is not like soil on Earth. It is the shattered remnant of eons of meteorite impacts, a powder of fine, glassy shards with edges as sharp as broken glass. Because there is no air or moisture to soften it, this dust behaves in strange ways. Under the relentless bombardment of solar radiation, individual grains become electrostatically charged, causing them to levitate and cling stubbornly to any surface, like a static charged sock fresh from the dryer. For a telescope array of millions of exposed antennas, this is a critical threat. A coating of this abrasive dust could physically degrade surfaces, interfere with delicate electrical connections, and completely obscure solar panels. Solutions must be as clever as the problem is persistent. Engineers are exploring materials with special coatings that dust simply slides off of, inspired by the way water beads on a lotus leaf. Others imagine tiny, built-in vibrations that shake the antennas clean at regular intervals, or even using electrostatic fields themselves to actively repel the charged particles away from sensitive components. The goal is not to fight the dust with constant human maintenance, but to design a system that can live with it gracefully, allowing the moon's own environment to become a manageable part of the design. The temperature extremes present a different, more brutal test. For 2 weeks at a time, the lunar surface bakes in unfiltered sunlight, with temperatures soaring past 100 degrees Celsius, hotter than boiling water. Then, as the landscape rotates into the long night, the heat radiates away into the blackness of space, and the mercury plummets to 150 degrees below zero. Any terrestrial electronics would be destroyed in a single cycle. The telescope's components must not only survive these swings but operate stably within them. This requires a symphony of thermal control. Engineers might use reflective, mirror-like coatings to bounce away excess sunlight, combined with layers of high-tech insulation that act like a super-efficient thermos. For the electronics, they could design closed-loop fluid systems that actively pump heat from warm areas to cold ones, maintaining a steady, survivable internal climate. But here, the vacuum of space adds a final complication. On Earth, excess heat can be carried away by air moving over a surface. On the Moon, there is no air for convective cooling. Heat can only escape through radiation, a much slower and less efficient process. This means every watt of power used by the computer processors and amplifiers must be accounted for and meticulously managed, their waste heat carefully radiated away into the void through specially designed panels. It is a balancing act of cosmic precision, ensuring the array's electronic heart keeps a steady beat through the long, silent lunar night. Overcoming these hurdles is not merely about making something work, it is about making it last. The scientific promise of this telescope depends on decades of uninterrupted, stable observation. A single major failure in the thermal system could freeze critical components beyond repair. A gradual accumulation of dust could slowly strangle its power supply. Each solution pushes the boundaries of what we consider possible for autonomous space systems. The resulting technologies, born from the need to listen to the universe's oldest whispers, will become the foundation for humanity's lasting presence on other worlds. They are the lessons in resilience we must learn to build not just telescopes, but sustainable futures in the stars. Such a monumental ear, built to listen across billions of years, demands a chorus of nations to bring it to life. The sheer ambition and expense of a lunar far-side telescope place it far beyond the reach of any single country. This is not a national mission, but a human one, a perfect catalyst for uniting the world's space agencies under a banner of pure discovery. The framework for this unprecedented cooperation is already taking shape with NASA's Artemis program. Artemis is far more than a series of crewed landings. It is a blueprint for a sustained lunar future. Its core goal of establishing a permanent, orbiting outpost called the Gateway and supporting surface operations provides the essential logistical backbone a far-side observatory would desperately need. Think of Artemis as the construction crew and supply line for the most remote scientific outpost ever conceived. The program's landers could deliver the massive rolls of antenna material or the fleets of deploying rovers. Its planned infrastructure, like surface power stations and orbiting communication satellites, would solve two of the telescope's biggest challenges. A dedicated relay satellite, positioned in a special orbit that can see both the far side and Earth, would act as a celestial switchboard, ensuring a constant stream of data flows back to scientists worldwide. Meanwhile, robust lunar power grids, potentially using nuclear systems for uninterrupted nighttime operation, could provide the steady, reliable energy needed to keep the array listening through the long, cold darkness. This is where global partnership becomes the engine of innovation. While NASA might provide the heavy lift and core infrastructure, international partners could contribute their unique strengths. One agency might specialize in developing the ultra-low power, radiation-hardened computer chips needed to process the flood of data. Another might excel at creating the autonomous robotics for precise antenna deployment and long-term maintenance. A third could bring expertise in the complex software algorithms required to combine signals from millions of separate antennas into a single, coherent image of the sky. The telescope itself would become a mosaic of global ingenuity, each piece reflecting the specialized excellence of a partner nation. Beyond the technical triumph, this collaboration carries a profound symbolic weight. In a world often divided, the project would stand as a towering example of what humanity can achieve when it works toward a common, peaceful goal. It would be a shared endeavor to acquire shared knowledge, answering questions that belong to all of us. The data it collects on the cosmic dawn, on distant worlds, and on our own sun would become a global commons, a gift to every nation and every future generation. This telescope, listening in the deepest quiet, could become the most powerful symbol of international unity we have ever placed in the heavens, a silent testament to our collective curiosity and our shared destiny among the stars. This perfect silence creates a profound communication paradox. To hear the universe's oldest whispers, we must build an observatory in the one place in the entire Earth-Moon system that can never see our planet directly. The far side is permanently turned away, hidden behind 2,000 miles of solid rock. This means every precious byte of data collected by the telescope, every faint signal from the cosmic dawn or a distant exoplanet, is trapped on a world with no direct line of sight home. Solving this is not a minor technical detail, it is the lifeline of the entire mission. We must build a celestial relay, a bridge across the void to bring the universe's secrets back to Earth. The solution lies in a gravitational sweet spot, a place where the pulls of Earth and the Moon create a stable point of balance. This location is called the Earth-Moon Lagrange Point 2, or EML2 for short. It is a point in space about 40,000 miles beyond the far side of the Moon. Here, a satellite can orbit in a kind of gravitational harmony, maintaining a perfect vantage point. It can always see both the hidden lunar far side and over the limb of the Moon, our distant blue planet. One or more relay satellites would be placed here, not in a simple circle, but in a graceful, three-dimensional halo orbit around this invisible point. Think of it as a cosmic switchboard operator. The telescope array on the surface would beam its collected data up to this waiting relay satellite. Then, with its large dish antenna pointed homeward, the satellite would forward the signal across the 250,000-mile gulf to massive receiving stations on Earth. This creates a two-hop interplanetary internet, a dedicated channel through the quiet, but the data itself is the real challenge. This is not like sending a few photographs. A telescope array composed of millions of antennas is listening to a wide range of frequencies with immense sensitivity. The raw data stream it produces would be a torrent, a flood of information that dwarfs the total traffic of the entire global internet. Compressing this data without losing the subtle, scientifically crucial details is a monumental computing task in itself. Then, that compressed river of ones and zeros must be transmitted with flawless reliability. The link must operate continuously through solar storms and orbital mechanics, with error rates so low they are almost unimaginable. Developing this robust, high-bandwidth communication system is as vital as the telescope's antennas themselves. It is the nervous system of the entire endeavor, ensuring that the silence of the far side is finally broken, not by noise, but by a stream of discovery flowing seamlessly to every scientist and curious mind on our waiting world. The true power of this lunar vision is revealed only when we compare it to the incredible tools we already have. Consider the most ambitious radio telescope project on Earth, the Square Kilometer Array. When completed, it will be a sprawling network of thousands of antennas across 2 continents, a masterpiece of engineering designed to listen to the cosmos. Yet for all its power, it fights a daily, unwinnable war against an invisible foe, the radio frequency interference from our own civilization. Its most sensitive observations require scheduling in the dead of night and rely on complex software filters to subtract the ever-present buzz of satellites, airplanes, and distant cities. It is like trying to hear a pin drop in a room where someone is constantly vacuuming. Even in the most remote deserts, Earth's own ionosphere, a shimmering layer of charged particles high above us, acts as a murky, turbulent lens. It bends and distorts the very low-frequency radio waves from the ancient universe, blurring the signal we seek into an indecipherable haze. For frequencies below about 30 MHz, which carry the stretched light from the cosmic dawn, the ionosphere becomes an impenetrable wall. Those whispers from the beginning of time simply never reach the ground. We have tried to rise above this problem by planning telescopes in space, like the proposed PRATUSH mission, which would operate in orbit around Earth. This is a tremendous step, escaping the blur of the atmosphere, but it is not enough. An orbital telescope still swims within the immense radiosphere of our planet, that expanding bubble of noise from every broadcast and radar pulse. It is like floating in a noisy ocean just below the surface, still surrounded by the churn. The lunar far side is different. It is not an incremental improvement, it is a categorical leap. By placing the Moon itself between the telescope and Earth, we achieve absolute radio quiet. This is the only location in the entire inner solar system that offers permanent, guaranteed shielding from every watt of terrestrial noise. Here, for the first time, the murky ionospheric wall vanishes. The telescope operates in the pristine vacuum of space, with an utterly clear view down to the lowest frequencies, the deep hum of the universe's infancy. This is the unexplored frontier of the radio spectrum, a band of cosmic history that has been both physically blocked and hopelessly polluted for all of human history. Accessing it is not about building a slightly better ear. It is about stepping into a silent library whose doors have been locked since the dawn of time, and finally being able to read the first pages of the story. These cosmic lighthouses offer a way to feel the fabric of reality itself bend and sway. Pulsars are the collapsed cores of massive stars that ended their lives in supernova explosions. What remains is a city-sized sphere of pure neutron star material, spinning hundreds of times per second with a magnetic field trillions of times stronger than Earth's. This combination acts like a cosmic beacon, sweeping a beam of radio waves across the galaxy with a regularity that rivals the most precise atomic clocks. A single pulsar's rhythm is a marvel, but the true power lies in listening to a choir of them. A lunar far-side array could monitor not one or two, but thousands of these stellar metronomes simultaneously, creating what is known as a pulsar timing array. Scientists would measure the arrival time of each pulsar's radio pulse with exquisite accuracy, building a galaxy-wide network of natural clocks. For years, even decades, they would listen for the slightest deviation in this perfect cosmic tick-tock. A pulse arriving a fraction of a millisecond early or late might seem insignificant, but it could be the signature of something monumental passing through. That something is a gravitational wave, a ripple in the very geometry of spacetime itself. These waves are generated by the most violent events in the universe, like the final inspiral and merger of two supermassive black holes, each with a mass billions of times that of our Sun, at the hearts of distant galaxies. As these waves wash through our region of the galaxy, they minutely stretch and compress the space between Earth and the pulsars. This incredibly subtle distortion alters the distance the radio pulses have to travel, causing those telltale timing irregularities across the entire array. Detecting this requires near-perfect silence and stability, which is precisely what the lunar far side provides. Earth-based pulsar timing arrays must constantly correct for the noisy churn of our ionosphere and the radio interference from our own technology, adding layers of uncertainty. The Moon's radio silence and the vacuum of space remove those filters, allowing for measurements of pristine clarity. This would open a new window onto the low-frequency gravitational wave universe, a domain invisible to ground-based detectors like LIGO. LIGO is exquisitely tuned to hear the high-frequency chirps from the merger of stellar mass black holes, events lasting fractions of a second. A lunar pulsar timing array would listen to the deep, bass hum of supermassive black holes, a signal that can take years or even decades to sweep past. It would allow us to hear the background chorus of countless mergers happening across cosmic time, mapping the growth of galaxies through their dark, beating hearts. Together, these different ears on the cosmos would give us a full symphony of spacetime, from the high notes of stellar collisions to the profound, rumbling overtone of the universe's largest structures dancing to the tune of gravity. Our galaxy is not just a collection of stars and dust, it is also woven through with invisible threads of force. A vast, complex magnetic field permeates the Milky Way, a silent architect shaping the very fabric of our cosmic home. This field guides the paths of high-energy cosmic rays, influences where new stars can be born, and sculpts the clouds of gas drifting between the stars. Yet for all its importance, mapping this magnetic tapestry has been a monumental challenge. We see its influence indirectly through a special kind of light. When fast-moving electrons spiral along these magnetic field lines, they emit a type of radio wave called synchrotron radiation. This light has a unique signature. It is polarized, meaning its waves vibrate in a preferred direction aligned with the magnetic field itself. By carefully measuring this polarization across the sky, astronomers can trace the field's invisible lines, much like iron filings revealing the shape of a magnet's influence. But from Earth, our view is fundamentally limited. The same ionosphere that blocks the ancient universe's signal also scrambles these delicate polarization measurements. The faint, diffuse glow from the galaxy's outer halo and its most tenuous regions is lost in the noise and distortion. A telescope on the lunar far side, operating in the pristine quiet and free from atmospheric blurring, could perform this mapping with transformative clarity. It would survey the entire sky at the low frequencies where this synchrotron glow is brightest, capturing the polarization signal with a sensitivity and precision that is simply impossible on our planet. This would not just give us a prettier picture, it would provide a three-dimensional magnetic map of our galaxy. We could see how the field twists and turns in the vast, unexplored galactic halo far beyond the starry disk. We could trace its strength in the faint bridges of gas between spiral arms, understanding how it holds these structures together or perhaps tears them apart. This detailed map would be a crucial key to one of astrophysics' great enduring puzzles. How are such immense magnetic fields generated and sustained over billions of years? Are they primordial, woven into the universe from its earliest moments, or are they dynamos spun up and amplified by the slow churn of interstellar gas and the rotation of the galaxy itself? By seeing the field's true geometry in its faintest reaches, we could start to distinguish between these theories, learning not just about our own Milky Way, but about a fundamental force that shapes every galaxy in the cosmos. The immense challenge of building in that silent, hostile environment guarantees a cascade of innovation. Every technical puzzle solved for this telescope will unlock new capabilities for our entire species, creating a legacy that extends far beyond astronomy. The most immediate breakthroughs will come from the robots tasked with construction. To deploy millions of antennas across miles of rugged terrain, we will need machines of unprecedented intelligence and resilience. These will not be the rovers we know today, remotely piloted with long delays. They must be truly autonomous, capable of navigating treacherous craters, diagnosing their own malfunctions, and collaborating as a swarm to complete a shared blueprint. The advanced computer vision, real-time decision-making, and cooperative algorithms developed for this purpose will revolutionize robotics on Earth. Imagine similar systems managing complex disaster response in hazardous environments, performing precision agriculture on a massive scale, or automating intricate logistics in vast warehouses. The lunar frontier will teach machines to see, think, and work together in ways we are only beginning to envision. Powering this endeavor through the 2-week lunar night is another monumental hurdle, one that will force a leap in energy storage technology. The solutions developed, whether advanced nuclear batteries or next-generation fuel cells, will provide a template for clean, reliable, off-grid power anywhere on Earth. Remote communities, disaster relief operations, and deep-sea research stations could all benefit from power systems born from the need to survive the Moon's extreme cold. Perhaps the most transformative spin-off, however, lies in learning to live off the land, a concept called in situ resource utilization. To build large structures affordably, we cannot bring every brick from Earth. Engineers are already experimenting with using concentrated sunlight or microwaves to melt the lunar regolith, turning that abrasive dust into solid paving slabs, radiation shielding walls, or even the foundations for habitats. Mastering this process of turning alien soil into useful material is the key to sustainable living beyond our planet. The same principles could later be applied to Mars, and the technologies refined for processing regolith may lead to new, efficient methods for recycling materials or manufacturing construction components right here at home. Then there is the invisible engine of the entire project, the software. The telescope will generate a flood of data so vast it would overwhelm today's internet. Making sense of that deluge will require a new generation of big data analytics and machine learning tools. Scientists will need algorithms that can identify the faint signal of a primordial hydrogen cloud buried in petabytes of noise, or spot the subtle pattern of an exoplanet's magnetic signature. These will not be simple filters, they will be intelligent systems that learn, adapt, and discover. The computational frameworks created to handle this cosmic data will inevitably filter into other fields. They could accelerate medical research by finding patterns in genetic databases, improve climate models by processing complex atmospheric data, or optimize global supply chains by predicting disruptions. The quest to listen to the universe will teach us how to listen to our own world's data in profoundly new ways. Ultimately, this project's greatest economic yield may be its inspiration. The Apollo program gifted the world not just moon rocks, but the integrated circuit, cordless tools, and modern water purification. It ignited a generation's passion for science and engineering. A lunar far-side telescope, a permanent outpost of human curiosity, would have a similar catalytic effect on a global scale. It represents a tangible, awe-inspiring goal that demands the brightest minds in robotics, materials science, software engineering, and systems design. It creates a pipeline for high-tech jobs and fosters international collaboration in cutting-edge industries. The story it tells is not one of short-term profit, but of long-term vision, demonstrating that humanity's most ambitious questions are also powerful engines for practical progress. The technologies spun off from this quiet listening post will weave themselves into the fabric of our future, proving that when we reach for the stars, we also build a better world right beneath our feet. This profound silence is not just a scientific opportunity, it is a wilderness. As we draw up plans to build humanity's greatest ear on the lunar far side, we must pause and ask a fundamental question. Do we have a responsibility to preserve the pristine environment we have found? This is not about protecting a landscape of rocks and dust, but about safeguarding a condition, a state of being. The far side is the most radio-quiet place in the entire solar system, a unique and irreplaceable resource for all of science. Establishing a major facility there, no matter how carefully designed, inevitably introduces a human-made signature. The landers that deliver the antennas, the power systems that run them, and the relay satellites that carry the data all emit their own faint radio whispers. The challenge is to make those whispers as quiet as possible, to be the most careful listeners we can be. This means the international community must come together to develop and enforce strict new protocols, creating the first rules for minimizing electromagnetic pollution on another world. We must treat the far side's radio quiet as a protected zone, a sanctuary for discovery. Every component must be shielded, every transmission frequency meticulously chosen and filtered, ensuring our own presence does not drown out the very signals we came to hear. The goal is to leave the vast majority of the far side's silence untouched, preserving its unique value for future generations of scientists who may build even more sensitive instruments. This sparks a much broader conversation about our role as stewards of celestial bodies. The moon has no atmosphere, no weather to erode our footprints or our debris. Our first footprints from Apollo are still there, perfectly preserved, and so is every discarded lander and rover. What we leave on the moon, we leave forever. This gives our actions a permanent weight. The urge to explore and utilize is a powerful driver of our species, but it must be balanced with a thoughtful duty to protect. We are not just visiting the moon, we are becoming a part of its history. How do we honor that responsibility? It means designing for sustainability from the very beginning, planning for minimal impact and long-term coexistence with the lunar environment. It means viewing these untouched realms not merely as resources to be used, but as archives of solar system history and as unique laboratories whose conditions are worth preserving for the science of tomorrow. The quiet we find on the far side is a gift, and how we choose to listen within it will define our legacy as a spacefaring civilization. The journey from a brilliant concept to a listening ear in the silence has already started. Right now, the project lives in the realm of advanced studies with funding from programs like NAS, Innovative Advanced Concepts, which nurtures ideas that sound like science fiction. This phase is all about answering the tough questions on paper, simulating the dust, testing antenna designs in vacuum chambers, and proving the core technologies could actually work. It is a necessary foundation, ensuring we are not just dreaming but engineering a viable future. The next decade will transform these paper studies into tangible steps on the lunar surface. We will likely see the first critical technology demonstrations, perhaps delivered by commercial lunar landers. A small rover might test new methods for deploying antenna film, or a stationary platform could measure the true depth of the radio quiet for months on end. Concurrently, the Artemis program's infrastructure will begin to take shape, establishing the power and communication networks that will one day support a far larger endeavor. This careful, phased approach is not a delay, it is the only responsible path forward. The logical next major milestone is a Pathfinder array, a small-scale proof of concept that could be deployed in the 2030s. Imagine a cluster of a few hundred antennas, not millions, planted by a single lander. This modest array would have two profound missions. First, it would serve as a final, ultimate validation of the far side's radio silence, listening with its own ears to confirm the theories. Second, and just as importantly, it would test every single survival skill in the lunar environment. Could its components withstand the temperature swings? How quickly does dust actually accumulate on its specially coated surfaces? Does the communication link through the relay satellite work flawlessly? The data from this Pathfinder would be priceless, a stream of engineering truth that would refine the design of the full-scale instrument down to the last bolt. Only after this successful shakedown mission would we be ready to scale up. The construction of a full kilometer-scale array, a true cathedral of listening, becomes a project for the 2040s or even later. This timeline reflects the sheer magnitude of the undertaking. It allows for the iterative learning that complex space systems demand, reducing risk with each step. It also aligns with the gradual development of the necessary heavy lift capabilities and autonomous robotics that will be needed to turn a crater floor into a scientific instrument. We are not simply building a telescope, we are growing an entire new capability for civilization, and that requires the patience to learn as we go. The first faint signals from the cosmic dawn may still be decades away from reaching our computers, but every year of careful work on Earth and on the Moon brings that moment of profound hearing one step closer. The true legacy of this lunar outpost may be measured not in petabytes of data, but in the spark of curiosity it ignites in a child's eyes. Beyond the profound scientific returns, this project carries an immense power to capture the public imagination and reshape education on a global scale. The very narrative of building a cathedral of listening on the Moon to hear the birth of the first stars is a story of epic human endeavor. It transforms abstract concepts in physics and engineering into a tangible, thrilling adventure. In classrooms from Tokyo to Buenos Aires, teachers could use this mission as a living curriculum. Students would not just read about radio waves or orbital mechanics. They could follow the deployment of antennas in real time, access live data feeds showing the telescope's current target, and interact with visualizations that turn the faint hum of cosmic hydrogen into a symphony they can hear and see. This connection makes learning visceral. A lesson on magnetic fields is no longer about diagrams in a textbook. It becomes about the invisible shield of a distant world that this very telescope is trying to detect. The story of the international team behind the mission itself is a powerful lesson in diversity and collaboration. Students would see scientists, engineers, and programmers from dozens of countries, speaking different languages but united by a single question, working together to solve impossible problems. This human element shows that science is a collective, inclusive pursuit, and that there is a place for every kind of mind in this grand exploration. That inspiration is the most critical payload. By motivating a new generation to pursue careers in science, technology, engineering, and mathematics, we ensure a continuous pipeline of brilliant talent for the coming space age. We foster a globally connected, scientifically literate society that values evidence, curiosity, and peaceful cooperation. The telescope's greatest discovery might be the countless future explorers it helps to create, the young minds who look up at the moon and no longer see a distant rock, but a beacon of human potential, silently listening to the universe and whispering back, "We are here and we are ready to learn." The scale of this vision inevitably invites a chorus of doubt, and rightly so. Building a cathedral of listening on another world demands we confront the immense price tag and the very real possibility of failure. Critics argue that such funds could build a dozen advanced telescopes on Earth, or that the treacherous lunar environment is too hostile for delicate electronics. These are not trivial concerns, they are the necessary friction that sharpens the mission's ultimate justification. The answer lies in one undeniable fact: the science this telescope pursues is not merely better, it is categorically impossible from anywhere else. No amount of funding or ingenuity on Earth can pierce the ionospheric wall to hear the stretched light of the cosmic dawn. That specific frequency band, carrying the universe's first photograph, is permanently blocked and polluted on our planet. This is not an incremental improvement. It's the difference between trying to read a history book in a silent library versus trying to read it in the middle of a roaring stadium. You simply cannot do it. The scientific return is therefore not just valuable, it is singular and irreplaceable, offering answers to questions that define our cosmic origin story. But the defense extends beyond pure astronomy. To view this project only as a telescope is to underestimate its purpose. It is better understood as the first permanent piece of scientific infrastructure on another world. The power systems developed to survive the lunar night, the autonomous robots that build and maintain it, and the high-bandwidth communication network linking it to Earth are not one-off gadgets. They form the foundational utilities for an entire new domain of human activity. This infrastructure would enable a cascade of other missions, from geology rovers that can operate anywhere on the moon to deep space biology experiments in shielded lunar caves. The cost and risk are not borne by astronomy alone, but are shared across future lunar science, commercial resource prospecting, and even crewed exploration heading to Mars. The telescope becomes the anchor tenant, justifying the initial heavy investment in roads and power lines that an entire lunar village will later use. In this light, the project transforms from a costly niche instrument into a strategic down payment on humanity's sustainable future in space, its value amortized across decades of discovery and development yet to come. That quiet answer would echo across centuries of human longing. For millennia, we have looked up at the stars and woven stories, wondering if other eyes were looking back. This telescope, in its perfect silence, offers the first real possibility of turning that ancient wonder into a definitive piece of data. The search for extraterrestrial intelligence has always been a gamble against a background of overwhelming noise. But from the lunar far side, the background drops to zero. The cosmic radio dial is finally clear. We could conduct the first truly comprehensive, sensitive, all-sky survey for the faint signatures of technology. We would listen not just for a deliberate message, but for the inevitable radio glow of a civilization that uses power and communicates, just as we have for the past century. The outcome, regardless of what we find, would reshape our understanding of reality itself. If, after years of patient listening from that most privileged vantage point, we were to detect a signal of unmistakable artificial origin, it would be the single most transformative moment in human history. The universe would instantly become a different place, a neighborhood. the philosophical, cultural, and scientific shockwaves would be unimaginable, answering our oldest question with a resounding no, we are not alone. But consider the other potential result, one that is equally profound in its implications. What if, after this exhaustive search from the one place we can hear perfectly, the cosmos returns only the natural chorus of stars and gas? That silence would be a discovery of monumental importance. It would provide our first solid, empirical data point suggesting that civilizations advanced enough to produce detectable technosignatures are either exceedingly rare, incredibly short-lived, or choose to remain hidden in ways we cannot yet perceive. This quiet would force a deep and humbling philosophical reckoning. It would underscore a profound solitude, suggesting that in our galactic neighborhood, the spark of technological consciousness may be a fleeting, fragile flame. This realization would not be a cause for despair, but for a profound sense of responsibility. If we are, for all practical purposes, alone in our capacity to wonder and to build, then the story of meaning in this vast cosmos is ours alone to write. The preservation of our pale blue dot, the nurturing of life and knowledge upon it, becomes a cosmic imperative of the highest order. Our achievements and our failures would carry the weight of the universe's only known witnesses to itself. This telescope, by providing a clear answer one way or the other, would force us to grow up as a species. We would have to confront our place in the cosmos not with speculation but with evidence. Either we find companionship in the darkness, forever altering our sense of kinship, or we confirm our isolation, forever cementing our duty as stewards of a rare and precious voice. That quest to know which reality we inhabit is the ultimate expression of an existential curiosity that has defined humanity since we first gazed at the night sky. The lunar far-side silence offers us the first real chance to hear the answer. This single radio telescope is merely the first instrument in a far grander symphony. The lunar far-side's unique environment offers more than just radio silence. It presents a pristine, stable platform completely free from Earth's shimmering atmosphere and electromagnetic fog. This makes it the ideal location not for one observatory, but for an entire constellation of them. We can envision a future where the far side is designated as a protected science preserve, a lunar Sagan observatory dedicated solely to peering into the cosmos. Alongside the vast radio array, we could construct massive optical and infrared telescopes. On Earth, our view of the stars twinkles and blurs as light passes through miles of turbulent air. On the Moon, there is no air at all. The stars would not twinkle, they would shine with a steady, piercing clarity. An optical telescope with a mirror built on the lunar surface could achieve resolutions 100 times sharper than the James Webb Space Telescope, seeing the surfaces of exoplanets as more than just dots of light. We might map clouds and continents on worlds light years away, in the frigid, permanent shadows of polar craters, where temperatures hover near absolute zero. We could place ultra-sensitive infrared detectors. Shielded from the sun's heat and Earth's thermal glow, these instruments could peer into the coldest, darkest nurseries of star formation within our own galaxy and detect the faint heat signatures of the very first galaxies to ever form. The synergy would be transformative. Imagine a gravitational wave detector using lasers in a quiet lunar vacuum, feeling a ripple in space-time. Within minutes, the optical scopes swing to the coordinates, the infrared eyes peer into the dust, and the radio ears listen for the afterglow. This is multi-messenger astronomy at its purest, observing a single cosmic cataclysm through every sense we possess, all from one stable, silent base. This vision redefines the far side from a barren wasteland into humanity's ultimate astronomical platform. Each new instrument would not start from scratch, but plug into a growing network of power, communications, and data processing established by its predecessors. A lunar science outpost would create a virtuous cycle where every discovery justifies and enables the next, more ambitious tool. It becomes a permanent campus for cosmic discovery, a legacy installation where generations of scientists, perhaps even working on site in shielded habitats, could conduct research impossible anywhere else. This is not a project for a single decade, but the foundation for a new age of understanding, a gift to the centuries of curious minds that will follow ours. The dream of this lunar telescope is a promise written in radio silence, a pledge to hear the story of everything. It is a story that begins with the first light after the cosmic dark and stretches forward to the magnetic heartbeat of distant worlds. This single instrument could answer questions that have haunted humanity since we first looked up, questions about our solitary place in the cosmos or the possibility of cosmic companionship. The path to building it is strewn with obstacles, from clinging lunar dust to the mind-bending complexity of constructing a city-sized ear with robotic hands. Yet the scale of the challenge is precisely matched by the magnitude of the reward. We are not merely solving engineering puzzles, we are learning how to live and build sustainably on another world, creating the very toolkit for our future as a spacefaring civilization. The scientific data would be priceless, but the inspiration it provides may be its most enduring legacy. It transforms our relationship with the moon from a destination to a gateway, a silent platform from which human curiosity can finally listen without distraction. As the Artemis program lays the first foundations and international partnerships take shape, we stand at the threshold of turning this audacious dream into a blueprint for reality. The cosmos has been broadcasting its history for 13.8 billion years. We have just begun to learn how to listen, and the quietest place we know is waiting for us to truly hear.